All right. Well, today begins chapter 25 on lipids. Guess I got that wrong in the heading here. We've so far been making our way through the major classes of biomolecules. We've talked about amino acids, peptides, and proteins, and we've also talked about carbohydrates. We can break lipids are generally molecules that are hydrophobic and nonpolar. And you can break lipids up into a couple different categories, two different groups. We've got lipids that are what we call hydrolyzable. That means can they be broken up into smaller molecules with water? And then you have lipids that are non-hydrolyzable. So we're going to go through each of these. Among the hydrolyzable lipids, you have waxes, which we'll talk about. You also have triglycerides. These are sometimes called triacylglycerols, but these are the fats and oils that we're familiar with. Don't know why ANS is plural there. Fats and oils. And then a related structure, sort of like the triglycerides, but different in an important way, are the so-called phospholipids. All of these have bonds that can be broken by hydrolysis reactions. And then you have other forms, other lipids that are not hydrolyzable, and these generally have different uses. These include the fat-soluble vitamins, eicosanoids, including prostaglandins. Eicosanoids and prostaglandins are used as signaling molecules. Terpenes, localized signaling molecules. Terpenes are found in a lot of different organisms, sometimes in the essential oils of various plants, but all over the place in many complicated hydrocarbon-based structures. And I'm going to put in parentheses here next to the terpenes steroids, because steroids in animals are derived from the terpene synthetic pathway. So let's just start with waxes, and to some extent this is going to be a bit of a survey. You'll need to be able to recognize structures based on structure, what kind of lipid the molecule is. A wax is basically an ester, and the ester has a carboxylic acid portion and an alcohol portion. And with waxes, both portions are long chain hydrocarbons. So here is a kind of wax that is isolated from the sperm whale. It's called spermaceti wax. And it's got 16 carbons, 2, 4, 6, 8, 10, 12, 14, 16 in the carboxylic acid portion. And then it has 16 carbons in the alcohol portion. 2, 4, 6, 8, 10, 12, 14, 16. So you've got a long chain hydrocarbon here and a long chain hydrocarbon here, a somewhat polar functional group, but the non-covalent interactions that this molecule can engage in are dominated by its nonpolar character. And so waxes are used often in places where organisms need the ability to be water repellent, to perform and also to avoid water evaporation. Many leaves in plants have a waxy coating that limits evaporation to conserve water. And there are waxes found in all kinds of different organisms. Okay, so there's not too much more to say besides that, but you should recognize a wax as having a carboxylic acid portion and an alcohol portion, the ester functional group, and the long chain hydrocarbon on either side. Next, and we'll spend quite a bit of time here, are the triacylglycerols, the fats and oils. We've talked about these before in chapter 3 of 351 when we talked about non-covalent interactions, and again in chapter 10 of 351 when we talked about alkenes and hydrogenation. A triacyl glycerol has this 3-carbon trialcohol portion, the glycerol portion, and then the triacyl portion comes from the 3 carboxylic acids that will be attached as esters to each of the oxygens of glycerol. So you've got that 3-carbon glycerol portion, an oxygen on each carbon, and then each of these oxygens is going to be tied up in an ester linkage with a long chain, what we will call fatty acid. And triacyl glycerols differ in the composition of the long chain fatty acid. 2, 4, 6, 8, 10, 12, 14, 16, let's say. So that's a 16 carbon. We're going to call that a saturated fatty acid because it has no double bonds. Each carbon is completely saturated with carbon-carbon and carbon-hydrogen bonds. Incidentally, for reasons we'll talk about later on in metabolism, all of the natural fatty acids and triglycerides have fatty acid components with even numbers of carbons. That's always true. And that has to do with how they're synthesized in the first place. And so these fatty acid portions can vary in composition. For example, suppose this is a 2, 4, 6, 8, 10, 12, 14, 16, now 18 carbon saturated fatty acid. But sometimes the fatty acid portion of the molecule has a double bond in the carbon chain, and that double bond in natural fatty acids is always cis. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Then a cis double bond, 9, 10, 11, 12, 13, 14, 15, 16. This is a 16 carbon fatty acid. It's mono unsaturated because it has one double bond, and that double bond involves carbons 9 and 10, and its configuration is cis. So we'll say that's a 9Z double bond. And so different triacylglycerides from different sources are going to vary in terms of the composition, the kind of fatty acid, number of carbons, number of double bonds. I just want to, we've talked about fatty acids before, but I want to make an important point and review an important point with you, mostly because it just has something to do with the way you experience the world around you. I'm going to write down the structures and melting points of various saturated fatty acids and unsaturated fatty acids. We're going to put melting point here. We're going to put number of carbons here. Sorry, getting myself confused. Number of carbons, melting point, and the location of double bonds. Whereas saturated fatty acids have no double bonds, so we won't have a column for double bonds there. So for saturated fatty acids, as we increase the number of carbons from 12 to 16 to 18 to 20, the melting point goes up dramatically. All of these fatty acids are solids at room temperature, but melting point increases dramatically as we add additional carbons. And the reason for that is, of course, straight out of chapter 3 in 351, the long chain hydrocarbon is able to engage in van der Waals or dispersion interactions with other long chain hydrocarbons. And the more those two long chain hydrocarbons can contact each other, the greater the surface area of each individual hydrocarbon, and the greater the ability of each individual hydrocarbon chain to get close to the other hydrocarbon chains. The stronger the van der Waals interactions, the more the more you have to increase the temperature to overcome those interactions, the higher the melting point will be. And that's an important concept that should be mostly review. Now, I want you to pay attention to what incorporation of a single or a few double bonds does to the melting point of various fatty acids. The 16 carbon fatty acid that I drew above with the double bond involving carbons 9 and 10 with a Z configuration has a melting point of 0 degrees Celsius. So this is a liquid at room temperature. Just the incorporation of that single double bond goes from solid to liquid. Why is that? Well, the kink in the backbone of this hydrocarbon with this cis double bond prevents individual hydrocarbon chains from packing against each other as tightly. That decreases the amount of contact surface area that two similarly monounsaturated fatty acids can engage in with each other. That decreases the strength of the van der Waals interactions between individual hydrocarbon chains. That means you don't have to add as much heat or increase the temperature as much to disrupt those weaker van der Waals interactions. And so the molecule goes from solid to liquid at a much lower temperature. And this is a fairly dramatic effect. It's true for the 18 carbon single double bond fatty acid as well, which has a melting point of 13 degrees. Some of these fatty acids have names that you may have heard of. The 18 carbon one is called oleic acid. The 18 carbon one that has two double bonds, 9Z and 12Z, has a melting point of -12. It's called linoleic. If you have three double bonds, that's 9Z, 12Z, and 15Z, that's also a liquid even below 0, and that's called linolenic acid. Naturally, as I'm writing this down, some of you want to know, are you expected to memorize those names? No, but you may hear them in your day-to-day life, and so we'll talk about them. There's a 20 carbon polyunsaturated fatty acid that has 4 double bonds, and its melting point is -50. This one is called arachidonic acid, and we will talk about that a little bit later. Arachidonic acid is a precursor to a lot of the eicosanoids, which are a class of non-hydrolyzable lipid. So what's to notice here? The more double bonds we have, the lower the melting point is. Again, the presence of the double bonds limits the contact surface area between individual hydrocarbon chains and makes it so that you don't have to overcome as many van der Waals interactions to go from solid to liquid, and therefore the melting point is lower. Couple general features of fatty acids, some terms that you may have heard before. I'm going to draw the 18 carbon linolenic acid. Excuse me. Okay, sorry, I started erasing. 1, 2, 3, 4, 5, 6, 7, 8, 9, cis double bond there, 10, 11, 12, cis double bond there, 13, 14, 15, cis double bond there, 16, 17, 18. So this is linolenic acid. There's the 9Z, 12Z, 15Z double bonds. Linolenic is an example of what is sometimes called an omega-3 fatty acid, where this is the Greek letter, the capital Greek letter omega, and not the character omega from the Bad Batch. What does that mean, omega-3 fatty acid? Well, as you recall, we assign the carbonyl carbon C, that's our reference position, and then carbons from there are sometimes given the Greek letters alpha, beta, and so on. Irrespective of how many carbons are in the hydrocarbon chain, the last carbon in the chain is called the omega carbon. Beginning and end, first and last, alpha and omega, and so on. So carbon 18 here is the omega carbon. And in linolenic acid, the reason it's called an omega-3 fatty acid is because there is a double bond involving the carbon 3 from the end, or the omega carbon. Okay, so an omega-3 fatty acid has a double bond 3 positions from the last carbon in the chain. And folks in food science, nutrition, dietetics could give us some information about the benefits of consuming omega-3 fatty acids. Some of the epidemiology perhaps related to whether it's protective or not in your diet for various cardiovascular outcomes. You will hear products advertised as being rich in omega-3 fatty acids, in particular eggs. What that likely means is they're feeding the chickens a diet that is rich in omega-3 fatty acids, and then that's getting incorporated into the various chicken eggs. Okay, I also want to talk about the fatty acid composition of various triacyl glycerols or triglycerides that you encounter in your day-to-day life. Some of this is in your text, and you can see here sort of the difference between fats and oils. So let's show you just some brief data. This isn't going to be organism specific. This is just animal fat or lard. In my mission in South Texas, lard was sold in a great big yellow 5-gallon bucket from the store H-E-B with the Spanish word manteca, and you could always tell the really good tortillas and tamales were made with manteca. Let's talk about the fatty acid composition of animal fat. This is what's in the triacylglycerol. We'll talk about the percent of fatty acids that are 12, 14, 16, or 18 carbons versus the unsaturated fatty acids. We'll talk about the 18 carbon 9Z composition versus the 18 carbon linoleic, which is 9Z 12Z composition of these various fatty acids or triacylglycerols. For animal fat, it's about 25%, the saturated 15 carbon, about 15% saturated 18 carbon, about 1% of the 14 carbon. Animal fat is about 50% the oleic acid, the 9Z 18 carbon chain, and then about 6% the linoleic, the 2 double bonds. So still a majority unsaturated, but a substantial composition of saturated, and most animal fats are solid at room temperature. If we switch to olive oil, you see a dramatic difference. So olive oil has only 5% of the 16 carbon and 5% of the 18 carbon saturated fat, 80% oleic acid, and 7% linoleic. So the big difference between animal fat and these numbers don't add up to 100 in part because there's other things that aren't written down here that are composition that make up the triacylglycerol as well. But you can see the big difference here between the animal fat and the olive oil is that olive oil is 80% oleic acid. And of course, olive oil, as you know, is a liquid at room temperature. Peanut oil is similarly about 7 and 5%, respectively, 16 and 18 carbon fatty acid chain, although peanut oil has 20% linoleic, the 2 double bond, 9Z, 12Z, 18 carbon hydrocarbon chain. So we generally call things that are solid at room temperature fats. Things that are liquids at room temperature, we will call them oil. Unless, of course, you're talking about coconut oil. And I don't have the breakdown of the different kinds of fatty acids, but for coconut oil, we're almost I don't have a breakdown of the individual kinds of carbon chains in coconut oil. I could look it up, but don't have it in front of me. It's about 86% saturated for coconut oil, only 7% oleic, and negligible amounts of linoleic. So coconut oil is mostly saturated fatty acids, which is why it tends to be a solid at room temperature, though if you heat it up, it can become liquid, which is of course true of the other animal fats as well. Okay, so if you want to look at table 25.3 in your text for some other fatty acid compositions of some well-known fats and oils, of course I don't want you to memorize numbers, but you do need to be aware of the fact that the more unsaturated fatty acids you have in a triacylglycerol, the more likely it is the triacylglycerol is to be a liquid at room temperature. Okay, let's talk about what types of reactions triacylglycerols can undergo. I'm going to just give you a general triacylglycerol structure. Whoops, did it wrong, didn't I? Depending on the triacylglycerol, all of these fatty acid chains could be the same or different. What does hydrolysis look like and how might that occur? Well, you could do it with water. You could use acidic catalyst. You could use bases for saponification. Think about how our ancestors made soap, and we've already talked about that. Or you could use an enzyme to do this. Enzymes that break the ester bond in triacylglycerols are called lipases. But the impact of the hydrolysis reaction is, as you know from hydrolysis of esters, to release the 3-carbon alcohol and the 3 long-chain fatty acids. So that should be review. That should not be surprising at all to you. Some other things that can occur with fatty acids, and I'm just going to copy this structure of a triacylglycerol because it's got a single double bond in it. This is an unsaturated triglyceride. You can use hydrogenation using hydrogen and palladium on carbon, and that will add hydrogen across the double bond of the triacylglycerol to convert what used to be an unsaturated fatty acid into a saturated fatty acid. And this reaction is called hydrogenation. So if you look at food labels, you will sometimes see the words partially hydrogenated vegetable oil or soybean oil, and all this means is that they have taken the soybean oil and subjected it to this reaction where they're adding hydrogen across the double bond. Okay. And this, of course, has the benefit of taking something that used to be a liquid or more liquidy and turning it into something that's more solid. And there's reasons you might want to have that be true for shelf storage and for ease in dispensing and cooking and so on. For example, peanut butter, peanut oil is a liquid at room temperature, and a lot of people don't like to buy peanut butter that has a thin layer of peanut oil at the top of the container. And so there's a couple different strategies, but one of them is to simply hydrogenate the peanut oil so that more of these unsaturated fatty acids come over here to the saturated portion, and then the oil is more of a solid, more of a fat, and will not separate from the other components of peanut butter. Of course, we mentioned perhaps in 351 how if this hydrogenation process is incomplete, and especially if it's done under reversible conditions, you can get some isomerization of the cis double bond to the trans double bond, and that's where trans fats come into play. Again, we'll let the nutrition, dietetics, and food scientists comment on exactly what the issues are with trans fat, but it is undesirable from many points of view, and so people have started to look for other ways to have the same sort of advantages. You will see food advertised as trans fat free, which doesn't necessarily mean that it has zero trans fat in it, just that it has lower than a set threshold established by the FDA. Okay, a final set of reactions that can occur to a triacylglycerol is oxidation. And this is associated with rancidity in fats and oils. And I've told some of you this story before, but in an oxidizing environment, it turns out the allylic CH bonds are weak and susceptible to what's called radical abstraction, meaning an unpaired electron, a molecule with an unpaired electron, can remove the hydrogen atom to leave a resonance stabilized radical. I'll leave it to your imagination as to what that resonance stabilized radical looks like. You should be able to draw it. That's not hard. That's a review of principles from 351 in the chapter 21 on radicals. But the resulting radical can go on to react with molecular oxygen, which itself is basically like a diradical, and ultimately give this organic peroxide, or what's called a hydroperoxide, which can undergo subsequent oxidation products, none of which taste or smell very good. So unsaturated fats and oils have a shelf stability problem because they can undergo allylic oxidation to give you hydroperoxides and other downstream products which don't smell very good, and that's when oil goes rancid. Some of you, I've told the story of the rancid tostada shells of 2017 or whatever year it was, when I was supposed to bring tostada shells to Grammy Sunday dinner at my mom's house, and I had one job, and that was to bring tostada shells, and I grabbed them off the shelf of our pantry, but they were kind of old, and everyone was eating their tostadas and saying, gee, that kind of doesn't taste very good. And this is why my parents lack confidence in my ability to execute simple tasks. No, they don't really. They trust me. But in any case, this is where oil rancidity comes from. All right, there's more we could say about fats and oils, but we should instead move on to talk about phospholipids. So lastly, I guess I want to say the purpose of triacylglycerols or triglycerides in biology is mostly energy storage. And so we will talk in metabolism about how triacylglycerols are in turn broken down into CO2 and water through the fatty acid metabolism, through glycolysis, and through the citric acid cycle. But stay tuned because we'll come to that later. All right, next on our list is basically a derivative of the triglycerides. These are called phospholipids, and phospholipids are like triglycerides, only one and only one of the esters has been hydrolyzed and replaced with something else. So I'm just going to draw a generic sort of 16 carbon saturated 2, 4, 6, 8, 10, 12, 14, 16 hydrocarbon chain. We'll do 2 of them. Of course, they might not both be 2, 4, 6, 8, 10, 12, 14, 16. They might not both be the same number of carbons. They might not both be saturated versus unsaturated, but there are 2 nonpolar tails. And then to the third oxygen is, it's no longer an ester. It's now, instead of an ester, it's a phosphoester. A phosphoester linkage between the third oxygen of glycerol and then a phosphate group. And I'm going to put an OR here. The phosphorus is doubly bonded to one oxygen and singly bonded to another, and that oxygen has a negative charge. And then the other oxygen usually has could have something attached to it, and we'll talk about what that oxygen is in a little bit. But this is a phosphodiacetyl glycerol, or a phospholipid. Okay, so let's talk about what that R group can be. The R group might just be a hydrogen attached to that oxygen, in which case we could draw sort of the phosphate head group. Oops. This is the oxygen that's attached to everything else. And of course, this would be in equilibrium with its conjugate base. The pKa of the singly negatively charged phosphate group going to a doubly negatively charged phosphate group is probably around 7. So you'd expect this to have either 1 or 2 charges. So when R is just an OH group, you have a molecule that has 2 nonpolar tails, which I'll illustrate with just the green sort of highlighting. 2 nonpolar tails. And then the head group is polar. And in this case, the head group would have either 1 or 2 negative charges. Okay, well, but the head group can be other things depending on what kind of organism you're in. If the R group is OH, the resulting diacylglycerol is sometimes called a phosphatidic acid. If the R group is instead I'm realizing probably that I should have just put R here since I've said the R was an OH. All right, and then this is our polar head group. Depending on what R is, it can sort of change the character of the polar head group. So sometimes R is this oxygen bonded to two carbons, and then the second carbon is bonded to an ammonium group. This two carbon one with an oxygen on one side and amino group on the other is called ethanolamine, and the resulting phospholipid that has ethanolamine is sometimes called phosphatidyl ethanolamine, which can be abbreviated as PE for people that are interested in lipids. And different organisms and different cell types have different compositions of phospholipids in their membranes. We haven't talked about the lipid bilayer yet, but that's where we're going. If R equals this same oxygen bonded to two carbons, but in this case the nitrogen is bonded to four methyl groups, or sorry, three other methyl groups. That group attached is called choline, and so the resulting phospholipid is called phosphatidylcholine, or PC. And then sometimes that R group, the oxygen is the side chain of a serine amino acid. So here is a serine amino acid. So what you're seeing is there are multiple ways to have polar head groups, and pay attention to the overall charge on the head group. One of the charges is from this negatively charged oxygen on the phosphate of the phosphoester, and then the other portion is this R portion. If it's phosphatidic acid, the overall head group charge can be either minus 1 or minus 2. If it's phosphatidylethynolamine, the overall charge is 0, and we call that a zwitterionic or zwitterionic head group. Same thing with phosphatidylcholine, the overall charge here would be 0, and again, phosphatidylcholine represents a zwitterionic head group. And then, of course, if it were phosphatidylserine, it looks like the overall charge here is minus 1 for phosphatidylserine, plus 1, minus 1, and then minus 1 there, overall minus 1. So different phospholipids have different types of head groups. Of course, if we take a step back and just consider the shape of a phospholipid, and we've done this before in 351, so this is definitely a review. This is the polar head group. These are the two non-polar tails. And you can see that the overall shape of the phospholipid is somewhat cylindrical in nature. The hydrophobic effect tends to cause these individual phospholipids to associate with each other in a way that prevents the non-polar tails from being exposed to water. We talked about why that was in 351. Non-polar tails tend to cause water molecules to lose a lot of entropy, become highly ordered, especially in the immediate vicinity of the non-polar tail. So there's an advantage to having these phospholipids line up with their polar head groups exposed to water. Of course, they can interact with water in a fairly productive way via hydrogen bonding and ion pairs. But this conical shape of the phospholipid leaves the backside totally and completely exposed to water, and so we can have one leaflet of phospholipids line up with another leaflet of phospholipids to form what's called a phospholipid bilayer. It's water on the one side, water on the outside, and this is the composition of biological membranes. And you have an edge of polar head groups exposed to water on one side, another polar head groups exposed to water on the other side, and then you have this nonpolar interior within the lipid bilayer. And things that cross membranes have to be able to get across the across both the polar head groups and the nonpolar interior. And we will, by this point, have talked about some membrane disrupting peptides and how they poke holes in this lipid bilayer based on the distribution of protein side chains that they have. Okay, the other thing to talk about, it's related to phospholipids. It's just sort of a quick aside, but there are some other molecules that can also be found in the phospholipid bilayer. You will encounter these in biochemistry. I want you to have seen them before. They are called sphingomyelins. They look like cousins of the phospholipids. The connectivity and the biosynthesis is totally different, but they have a strong resemblance. So what I'm going to draw for you now is an example of a sphingomyelin. Okay, just trying to make sure I get the number of carbons right. Hopefully, as I draw this, you can see the resemblance to some phospholipids. For example, notice the ethanolamine, the phosphate-linked ethanolamine head group that is common to other phospholipids. Also notice this long chain hydrocarbon. It's not linked to glycerol via an ester linkage. This long chain hydrocarbon is part of the same chain that's connected to the phosphate group. So it's different from a phospholipid, but in terms of nonpolar character, it's pretty close. Then this nitrogen is itself tied up with a long chain hydrocarbon via an amide bond. So I'll draw a 2, 4, 6, 8, 10, 12, 14 carbon chain. So for sphingomyelins, you have this long nonpolar tail here, and you have this other nonpolar tail here. But these can integrate with the lipid bilayer in the same way that a phospholipid can. It's just like one of the two chains is different from the other. Okay, next I want to say a little bit about a class of molecules called eicosanoids. I want you to be able to recognize these as such, though I don't particularly care that you know what kind of eicosanoid is what. So the eicosanoids are so named because they are derived from a 20 carbon precursor, and that eicosa is a Greek prefix for a 20 carbon precursor. So here is the precursor that's common. It's called arachidonic acid. And it has this basic structure. Okay, 20 carbons. And there are various enzymes that can take this single precursor and turn it into different things. For example, a class of enzymes called cyclooxygenases among which are COX-1 and COX-2 are used to convert arachidonic acid into a more complicated but unstable precursor. There's a 5-membered ring here. You can see why these are called cyclooxygenases, because the molecule is cyclized and there are oxygens on these 2 carbons that didn't used to be there. And then, of course, this conversion is not meant to make sense. You're not meant to see the actual reaction or how it happens. I'm just showing you what happens so you can get an idea of where the 20 carbons go. This is called prostaglandin G2, and it's an unstable precursor, but can be converted through various biological processes into some of the following outcomes. So one, oops, got the stereochemistry wrong. Is here. This is called PGF2 alpha, prostaglandin F2 alpha, and prostaglandins have various effects. They in part lower blood pressure, they can inhibit platelet aggregation, they are involved in controlling inflammation, involved in gastric secretions, they're involved in stimulating uterine contractions, and can relax the smooth muscles of the uterus. Prostaglandins themselves are involved in pain and inflammation, and so there are various drugs that target the cyclooxygenases as inhibitors to treat pain. The most well-known are the non-steroidal anti-inflammatory drugs, NSAIDs, like ibuprofen and aspirin, and these target COX-1. They inactivate the COX-1 enzymes. But that often has the byproduct of increasing gastric secretions, which make people that take a lot of aspirin and or ibuprofen potentially susceptible to ulcer formation. In the late 90s, a group of inhibitors to COX-2 were developed under the trade names Vioxx and Celebrex by Merck and Pfizer and others. These inhibited the COX-2 enzyme. The COX-2 enzyme was discovered here at BYU by Professor Dan Simmons, who taught biochemistry when I was a student here. And it was thought that these could be better treatments for pain because they sidestepped COX-2 inhibitors didn't increase gastric secretions. And so some of these drugs were on the market for quite a while until they were pulled from the market in the mid 2000s because of an associated risk with increased risk with heart attack and stroke. Okay, there are a few others that fall into this category. Again, I just want you to recognize they're complicated structures, recognize that they all come from the same 20 carbon precursor. So this is an example of a prostaglandin. There are a lot of drugs that mimic prostaglandins that have specific uses, such as inducing labor. A related class of molecules, which is really weird, you're going to love this because it has your favorite, a 6-membered ring on it, are called thromboxanes. You've still got sort of the same number of carbons but arranged differently, and with a weird 4-membered ring containing an oxygen. Other than that, the structure is pretty similar, but that small change in structure has a fairly dramatic impact in activity. So this is a thromboxane called TXA2. The in thromboxane tells you this is going to have to do with blood coagulation. Thromboxanes generally constrict blood vessels and trigger platelet aggregation. So that's sort of what you want to have near a site of bleeding. You don't want to have constricted blood vessels and platelet aggregation in your heart. And so that highlights one important thing about thromboxanes. They are used to signal processes, but their activity, they are synthesized very close to the desired site of activity. You don't want these floating around in your blood like hormones that are synthesized in one location and then transported through blood to a very distal location. It needs to be fairly localized. If you change the structure a little bit, so what we're going to draw now looks like a little bit of a hybrid between a thromboxane and prostaglandin. You've got this 5-membered ring with an additional bond to it, an oxygen here. The lower portion is going to look the same as the prostaglandins and thromboxanes, but the upper portion is different. And this is called PGI2, which is an example of a prostacyclin. Prostacyclins dilate blood vessels and inhibit platelet aggregation. So that's exactly opposite the activity of a thromboxane. One last thing to say in this category of eicosanoids while we're on the subject is there's another enzyme called 5-lipoxygenase, which converts the arachidonic acid into something else entirely, which I'm going to draw here. One double bond is still cis. Then you have these 3 double bonds that are now, one is cis but 2 are trans. Carboxylic acid here, that's your 20 carbon chain. We've been oxidized there with an OH group. Then you've got a sulfur here, and then that sulfur appears to be a cysteine side chain. With glycine on this side. And then I need space to draw the rest of it. Then bonded to this nitrogen is a glutamic acid side chain carboxylic acid. And this is called LTC4, which is an example of a leukotriene. How can you tell something's a leukotriene? Look for the triene, the 3 conjugated pi bonds. Leukotrienes are involved in constricting smooth muscle, especially in the lungs, and so leukotrienes are targets sometimes for asthma medication. So again, the point is, a simple precursor or decently simple precursor leads to these complicated outcomes through different enzymes, and they have different activities. And again, because prostaglandins, thromboxanes, prostacyclins are often they're local acting, they're synthesized close to the site of action. They have relatively low half-lives. That's good, because if you want to aggregate platelets, you want that to occur at a fairly local spot near the wound and not everywhere. Okay, so with that, I guess the one more thing I want to do is to, nope, we'll just pause there. That is a good stopping point for this first portion of the June 3rd lecture.